the goal of this presentation is sort of give you guys a peek under the hood of how the SambaFlow Compiler works and what are all the things it does, and just sort of give you guys an overview of the compiler technology that we have developed so far. So as Vijay presented, roughly speaking, our Samba for PyTorch compilation is broken into these 4 major components. First is this Samba PyTorch API. So for folks who are familiar with the compiler, you can think of it as sort of our compiler front end. The job of the Samba component is basically to extract the model graph and constructs the model IR as internal IR. And then it goes through the compiler to generate the executable, and then it also takes that executable and run it on the RDUs. So in terms of the compiler, we actually have, you can think of as 2 separate compilers. One of them is a graph compiler. This is sort of used for graph level optimizations and transformations. And then we have a kernel library, and these are for implementing. These are sort of to take the transform graph to actually map onto the actual RDUs and devices. So another key component here is a kernel library. So for a lot of the operators, especially for the high compute ones, such as matrix multiplication, we actually have implemented our specific libraries that are really efficient and sort of uses all the various different stages of the ALUs that you've seen in the PCU diagram that Vijay shown before. And part of the job of the kernel compiler is basically linking these libraries and with the model graph itself and combining together to form the final executable. So in terms of PyTorch support, just a little bit of overview. We support BF16 and EPS32. The list of operator we support, we have a document you can refer to. And in terms of foundation model, I think there were a few questions about that. We have actually tested and run various different foundation models on our architectures. So so here's all the models we have actually run on our architecture we have tested. Obviously, there's many other foundation models that are ones that are listed here. We can't really run every single one of them that actually come out. The ML industry is moving really fast. Specifically for the ones that we have actually run and verified the accuracy are the GPT, Bloom, and Hubert. And because a lot of these foundation models are very expensive to run and verify. So for the other ones, we have run them, we have sort of verified components of them, but we have never run it with real data set, with real checkpoints. So this is what we call functionally verified. And in this bucket, we have VIT, T5, NeoX, and Llama, and OPT. Okay, so how does the PyTorch model actually gets transformed and map onto our PCUs and PMUs? So so this is sort of the life of a model on RDU. You start out with a PyTorch model, and after so Samba is like I said, you serve as a front end. You trace it through the graph to generate this IR. Here, for example, each node is represented one PyTorch operator, such as gem or relu, and the IR basically is sort of this data flow graph. So the first main component of the graph compiler is graph decomposition. And here, there are actually multiple different ways you decompose a graph. Here, the 3 main way is what we call O0, O1, and O3. So in O0 mode, what it is sort of you take the graph and you break up every single PyTorch operator into its own subgraph. And that's basically what we're showing here. So let's say this is your graph, and it's basically decomposed into different PyTorch operators. And each PyTorch operator is its own subgraph. And in addition, you will formulate a execution schedule. So in many of the ML model graph, like the same operator is used multiple times. So that's why there's this, you can think of this execution or call graph. And then you have these three different operators. So this is sort of the basic the base model of execution. And in O1 is basically looking at this graph and fusing various different operators together. So so here you can, for example, maybe you want to fuse a gem with a ReLU. So then both the gem and ReLU will be formulated into the same graph rather than having them to be two separate graphs. And then in addition to that, we have the O3, which is sort of whole graph optimization. So this is taking the entire graph and looking at that as I'm trying to compile the entire graph at once. So obviously there are trade-offs, right? So O0 is basically for functionality. In this mode is quickest to compile, but obviously it's lower performance. You're not utilizing a lot of the advantages of the data flow by merging the different operators together. But this is sort of easier to bring up and easier to debug, right? So that's O0 mode. And in O1 mode is basically, you're starting to merge different nodes together. So currently with our compiler stack, you still have a stable compilation, but currently we're working on various different performance optimizations and improving the performance of O1. And O3 is basically you're taking the entire graph, and then this will result obviously in even higher performance. But again, this currently does not work for all the models. There's a lot of complexity related to trying to optimize an entire ML graph. So currently so these are the three different options. O0 is the most stable, and O1 and O3, you can think of this as more and more aggressive optimizations. And finally, we have this thing called O3 with HD. So this is basically, you're taking the entire graph, and then you sort of override some of the compiler decision with manual optimization decisions. This gives you the maximum performance, but obviously this requires a lot of manual hand tuning. And one of the caveat currently is that the HD file currently is provided by SambaNova. And I'll touch on this a little bit later. We're not with the current release, but in one of the future releases, we're planning on starting to release some limited form of this HD so that user can also play around with overriding some of the compiler decisions. So so once you have this graph, you broke into very different functions. So the first thing it does is sort of training support. This is, again, if you want to compile the model for training, you will do autograd and generate the backward graph corresponding to each of the graph. And again, the execution schedule will be added for the backward execution graph. And after you do that, you generate the full graph and the backward graph. The second thing it does is sort of graph optimization. So this is where a lot of the complicated optimization happens. So sometimes we decide we take the model and we take each of the operators. We decide what's the power factor, how many PCUs and PMU are using. And we decide the tiling factor. If the tensor is too big, we sort of chop up the tensor into smaller pieces. So all of these happen within the graph optimization stage. So there are some known limitations currently. So with the current release, operator parallelizations is restricted to one RDU. In order to utilize multi-RDU parallelization, this actually does require a manual HD file if you want to map a particular operator across multiple different RDUs. And this is actually one of the things we're working really hard on right now. And with the next release, we actually aim to release a feature where you can actually automatically parallelize across multiple RDUs. By the way, feel free to stop me anytime to ask me questions about any of this. Because I have this in the full presentation mode, I don't see any of the questions. So if you have any questions about this, please just interrupt me and ask. So after you do the parallelization, you define you do the you parallelize, you define the parallelization factor. Then you lower each of these functions, this operator subgraph, into one or more sections. So one section is basically the basic unit of computation that runs on RDU at one time. Sometimes one of these subgraphs just map directly into one section. Other time, because the graph is really big, or there's a lot more compute than what can be supported on one RDU, the compiler will then chop it up into multiple different sections, and so that whatever is in one section can guarantee to run and map onto the RDU. So up to this point, everything is still based on you can think of it as still mathematical and or mathematical operations, right? So from this point on, this is where the connection with kernel libraries come in. When you do this graph lowering, then you're no longer talking about PyTorch or a mathematical operator. You're more talking about the SambaFlow implementation of those realization of those operators onto the PCUs and PMUs. So this is where you start this is where the compiler start formulating the data flow pipelines, and for each of the sections, the compiler will construct a data flow pipeline, and then you will also invoke the kernel library to transform these mathematical operators into the SambaFlow implementation of them. So for example, this one, every single operator node here will be maybe a set of PCUs and PMUs, and this will all include the PMU programming for that particular unit. And then finally, this is where we link to the kernel compiler. So at this point, your mathematical graph is basically transformed into a set of connected PCUs and PMUs into this data flow graph. And this is the main job of the kernel compiler, is basically mapping the PCUs and PMU graph onto the physical PCU and PMU units. So this is so sometimes you hear the term place and route. So this is you have these this graph, and the job of a PNR is basically picking the placement of each of these PCUs and PMUs onto the physical PCUs and PMU units. And there are a bunch of other stuff that are done in the kernel compiler, but after that, you finally generate the bit files and paths, and this is sort of the executable. And again, what this executable or path consists of, it consists of the bit file, the programming of each of the sections. It also contains the tensor memory allocations to the DDR memory, and it also has an execution schedule, right? And various other information. So this is the whole thing is called a path, and this thing is then when you run it, this thing is then given to the runtime to run that on the RDUs. One section at a time. So what are some of the things that we're currently still working on the compiler side? So first, obviously, performance improvement. Performance optimization is never done, and as you all know, performance optimization is a really hard problem. So we're still looking into improving the performance. So out of the box, you utilize the PCUs and PMUs you have on the chip. So this is one of the key things that we're currently working on. And another feature is, like I mentioned before, this multi-RDU auto parallelization support. So you can take an operator or a subgraph, I should say, and map onto up to 8 RDUs. And the other thing we're working on is other PyTorch operators. And one of the key features we're working on supporting is flash attention. And as I mentioned before, there's this HD API. So this is basically controlling and overriding various different compiler decisions. Currently, we're looking into figuring out a way to robustify that and releasing that as a HTTP, so the programmer can also override some of the compiler decisions themselves if they choose to. You know, obviously SambaTune, which we'll talk about in a later presentation, but we are also working on a better programming API as well. So currently, as we mentioned before, you would have to take the PyTorch model and then transform it in Samba using SambaFlow and then run that. There is another pre-production tool that we have. It's called it's actually it is using just-in-time compilation. So in this way, you would just take a PyTorch model without any changes, be able to run it on RDU. So so this is currently in pre-production where it's not ready for release, and we have some but this will the point with this JIT is basically it makes it much easier to run code on our make it much easier to develop and bring up models to run on RDU. And in addition, we also have the C++ API, but again, these are still not ready yet for final release.